Hello, everyone. Welcome to our first seminar of 2026. Happy New Year. And I'm very honored to introduce our first speaker of the year, Dr. Shravan Hanasoge. Professor Shravan Hanasoge is a professor in the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research and a co-principal investigator of the Center for Astrophysics and Space Science at New York University, Abu Dhabi. He received his PhD from Stanford University and held postdoctoral positions at the Max Planck Institute for Solar System Research and Princeton University. Professor Hanasoge's research uses helioseismic and astroseismic techniques to image the internal structure and dynamics of the Sun, stars, and the Earth. His work includes helioseismic tomography, normal mode coupling to probe convection and Lorentz stresses, and machine learning methods to extract physical patterns underlying magnetic processes such as flares and flux emergence. Today, he will give a talk about helioseismic evidence for thermal and magneto-Rossby waves. Shravan, you have the Zoom now.
Right. Thank you very much. Thank you. Very, very kind of you to introduce me and also invite me to this to give this talk. Okay, so let me begin. So these are, first of all, these are two foundational problems in solar physics: the search for thermal Rossby modes and or thermal inertial modes and magneto-Rossby modes. And so I want to emphasize that I'm just providing evidence and dispersion relations that I'm recovered from seismology that to conclusively or definitively say that these are either thermal or magnetic inertial modes will require more work and potentially independent types of measurements. Okay, so I just did a quick scan of the audience. There's many experts on these topics. Peter Gilman's here, so I'm very, uh, intimidated by his presence, and he's done quite a bit of work on these topics as well. On both of these topics, and in fact, I've referred to Gilman and Glatzmeyer and Gilman and Fox and all of these papers over the previous century, and so they've really done extraordinary work on these topics. So what are inertial oscillations? So these are oscillations where Coriolis force plays a very important role, and so their frequencies are therefore comparable to that of rotation, subrotation, or maybe factor of 2 or 3 times rotation rate. And ostensibly they're very, very important in maintaining the overall angular momentum transport in the sun. And if you were to believe a lot of the theoretical work that's come out in the last few decades, 2 decades, or maybe 3 now, these is there a chat here?
Sorry, that's just me. Keep going.
Okay, okay, all right. Hi, Shay. Yeah, so they basically modulate the dynamo, introducing timescales, periodicities, and they also, influence flux emergence. So, they sort of jostle magnetic field at the base of the convection zone or wherever they're trapped. And by the time they emerge, they move to a certain or to a different position because of the wave itself. So there are a number of aspects that these inertial oscillations influence. And as a seismologist, we're very interested because they're very highly sensitive to the adiabaticity, to these other parameters that P modes are not necessarily that sensitive to. P modes are sensitive to differential rotation, of course, but I think inertial oscillations are probably even more sensitive to differential rotation than P modes, and certainly viscosity and so on. They can really be useful in constraining these parameters. So in all of this work, okay, sorry, yeah. So in all of this work, basically inertial modes need to be, in order to detect them, we use P modes to sense their presence. And so if you were to think of the sun, of course, it has flows in a variety of time scales and spatial scales. And one of those is the inertial mode flow itself, or the motions associated with inertial modes. They're very weak. They vary with time. They're periodic, of course, and as I said, their flows have frequencies, or they vary on time scales comparable to the rotation time, or probably longer. And so the way that we use normal mode coupling, which is a helioseismic method, which I'll describe briefly here, is the first step is to take the vector flow on the sphere in the three sphere, and you do a Helmholtz decomposition of this. And so you broadly retrieve two parameters, or two types of flows: toroidal flows and poloidal flows. Sorry to jump into the technical stuff, but I might as well get into it. And this is the way by which the whole analysis proceeds. So toroidal flows are they're basically restricted to on the two spheres, so they're restricted on the lateral surfaces at fixed radius. And because they have no radial motion, they have to be mass conserving by construction. And so they have a v theta, v phi, and they're sort of restricted in that two space, in that two sphere. And basically, you could think of it as radial vorticity, right? So you have um, I mean, that's what a toroidal flow is. It's radial vorticity. The vorticity in the radial, projected onto the radial direction, and those are the motions associated with it. And in contrast, poloidal flows are basically convective. They have a radial and horizontal. They have radial and horizontal flows, and if you wish, you could constrain. You could introduce mass conservation as a way of connecting the radial horizontal flows, but they don't necessarily need to be. There are three independent parameters basically in poloidal flows. Okay, so the idea is that I use P modes to measure various seismic quantities, which are then connected directly to these two types of flows, toroidal and poloidal. Okay, and so what I use is normal mode coupling, which is an absolutely fantastic method that Martin Woodard. I'm sorry, this presentation I sort of hastily put together, so I haven't referenced people appropriately. But there's by no means am I suggesting that I'm introduce any of the stuff. It's Martin Woodard and a variety of other people in terrestrial seismology who've introduced these concepts. And that, as I said, this is not properly referenced and not properly cited numerous contributors. So please do not assume that I'm saying that I'm introducing any of these concepts. Most of these have already been discussed or introduced or studied before. So Martin Woodard, about 30 years ago, came up with this method, borrowing it from terrestrial seismology, but making very important distinctions that are actually only relevant for the sun, and that in fact have not been included in the terrestrial counterparts. But so the idea is based ultimately on a quantum mechanical way of thinking about systems, and that you take a simple reference system for the sun, and so going back to the sun, for the sun you take a non-rotating, non-convecting, static, non-time varying system, which is a sphere. I mean, and that's your reference model, and that's model S, for instance. And so if you take model S and you look at the wave operator for the linear wave operator for this standard model, then this model has a complete and orthonormal basis, and which is to say that any function then in the sphere can be expressed as a linear combination of these eigenfunctions. But of course, as we know, the sun is actually rotating. It has convection, it has magnetism, it has highly non-axisymmetric structure, and is time varying. So therefore, I mean, evidently the eigenfunctions, the eigenfrequencies are different from these models, but so are the eigenfunctions. And the eigenfunctions of the sun are distinct from the reference model, from those of the reference model. But because we have orthonormality and completeness, we can express ostensibly the eigenfunctions of the sun as linear combinations of the reference model modes. And so it is in this context that when I say normal mode coupling, that's what I mean, that that the modes of the sun are coupled with respect to the reference model modes. So every mode of the sun is a combination of a few of the reference model eigenfunctions, and so they're coupled. So the reason why it's such a fantastic method is that first it relies on normal modes. So these modes contain sort of the full seismic information. And then secondly, there's virtually no data processing. So there's no smoothing. There's very little stuff that you need to do. So we just take the spherical harmonic time series from HMI. We take stuff from Gong, and in this case, these are the sort of the time periods that I've indicated here that I've taken. These data are beautiful. They're really well, from the raw HMI observations have been processed very nicely and then produced, and they're easily available, and they're very high quality observations. And similarly with Gong plus plus as well. So it started with 2001 because that's when Gong upgraded. And when I started this, I just assumed that HMI is superior to Gong. I don't know why I assumed this, but it's really not the case. As I discovered, Gong is actually really quite a superb instrument, produces really high quality inferences as well, as you'll see in the subsequent slides. So the basic measurement that I use that in all of this is the unit measurement is this cross correlation in harmonic domain. So you have the spherical harmonic time series, you transform that into the Fourier domain. So you're fully in the harmonic domain then, the Lm omega. And so you take a correlation of one quantity, the cross correlation between two different indices in the harmonic domain. And so you see there's an M prime and M. And so that the difference between M prime and M is something that we call T. That's the azimuth. So perturbation of order azimuthal order T would introduce a correlation between M and M prime, where M prime is M plus T. And you see an omega and omega prime here. So this is omega and let's say omega plus sigma. And a perturbation of whose inverse time scale is sigma would introduce a correlation between omega and omega prime. And L and L prime are okay, they're also connected, but these are the two primary quantities, the azimuthal the order and the temporal frequency of that perturbation basically induces these correlations. And so this is the great power of mode coupling. It's just this simple measurement, this seemingly trivial measurement encodes an incredible amount of information, this two-point correlation. And this is also something that the terrestrial seismology people have not done, but Martin Woodard has engineered this measurement. So many congratulations to him for he just didn't see it through to its logical conclusion, but all of the foundational work was introduced by Martin. Okay, so you take these correlations, you do a lot of algebra, but straightforward algebra. It's tedious, but it's very straightforward. It uses something called generalized spherical harmonics, very well understood. Is basically rotation groups on a sphere, tensor rotation on a sphere, etc. So these are very straightforward in a mathematical sense. They're very well understood. And you do a bunch of algebra and you reduce this problem. So first, this quantity, the phi star phi, is a very big quantity because you have 1, 2, 3, 4, 5, 6 different parameters. So it becomes a huge object. So Martin introduced something called a B coefficient, which is a way to simplify all of that large amount of seismic information. A lot of it is very noisy. So this B basically, as I said, this is the difference between sigma is the difference between omega prime and omega. T is the difference between M prime and M, and S is the harmonic order of the perturbation. So ST and sigma represent the harmonic indices of the perturbation, right? So if you have a flow that's varying on with a harmonic order of S, azimuthal order of T, and sigma is its temporal frequency. So now you make this measurement from these observations. There's some process by which straightforward linear process by which you take this, you compute this, then you move it into this B sigma. And then from that, you can connect that through this inverse theory, and you say that's connected to these are poloidal flows, UST, and WST are the toroidal flows. So this is the radial vorticity, and this is the poloidal flow. Okay, so this is all very well understood. I'm just introducing all of this. Has been documented numerous times in many papers over the past 2 decades. Very well understood. There's nothing new here so far. So in this analysis, I have restricted myself to same L, which means L prime. We saw this L prime equal to L. And the reason I do that, and same radial order. So of course, in this, there's no radial order, but omega is a proxy for radial order. And so when I say radial order, I mean, I'm basically looking at the same mode, and I'm looking at the cross correlation of the mode slightly offset in temporal frequency. And so this is a very well studied measurement. There's a very nice properties to it. There's in helioseismology, you have this rotational aliasing. So I mean, for those of you who are non-helioseismologists, you may not know about it. So I won't really get into it. But for those of you who know it, you already know it. So the nice thing about using mode coupling, same L mode coupling, is that there is no aliasing in the plus minus omega sun in those two windows, in the prograde and retrograde windows. You don't alias. So you can actually independently image both the full subrotation prograde and the subrotation retrograde without worrying about one thing going into another. And the reason you're able to do that is that uh, you can it's only doing it at odds harmonic degrees. We're not able to measure. So S, this is this quantity S. You can only measure it at odd harmonic degrees. So this idiosyncrasy basically allows this. So these two are connected basically somehow through some mathematical analysis. You can derive this. But the other negative thing is that you can only image radial vorticity. So you can't really get poloidal flows in this, which, as I said, all of this is just evidence, the analysis now. That's it. I'm done explaining the analysis. I'll show you the results now. But all of the results basically are just evidence. They don't really, you need to do more to really confirm that these are as I say they are. And you can't really, with these methods, with these measurements, you can't image divergence. You need to look at finite L prime minus L differences to do that. Okay, so this is something that I might potentially do in the future. Okay, so that's the seismology method. And so let me jump into thermal Rossby modes. I love this result a lot more than I like the magneto-Rossby waves. It's just fantastic stuff, but none of the journals seem to like it very much. So it's accepted now. It's in APJ letters, but I tried all the other ones. They were not impressed at all. But I really thought that this was the nicest result. Anyway, so these were predicted a long time ago by Roberts and Bussa and Gilman and a variety of others. Again, I apologize for not citing. There's been so many people who worked on this topic, who worked very deeply on this, thought very deeply on these modes and what they say about convection and how they're born and why they originate, etc. And well, the reason that they've risen to the fore in more recent years is that numerical simulations seem to show columnar features. They're very strong. In fact, much more so, they're much more strongly present than passive Rossby modes. Passive Rossby modes are very weakly present at the surface of the upper layer of these numerical simulations, although perhaps the numerical simulations themselves have gotten more advanced. So I should say that my knowledge may be a little dated on this. But they're columnar convective cells, and these are called these Bussa columns, and they're parallel to the rotation axis. And because they're rotating this way, they have a radial vorticity pointing outwards potentially in the northern hemisphere and pointing inwards in the southern hemisphere. So they have opposite senses of vorticity. But we haven't seen it. So the interesting thing is that we've seen passive Rossby modes like the Rossby-Horwitz like mode in observations, but they're not seen in numerical simulations very clearly. And but numerical simulations have seen these Bussa columns, but we've not seen them in the observations. So there's some strange disconnect there. But the other thing I want to say is Heinemann and Jane have said that some of these features, these Bussa columns, appear in the spatial domain, but don't necessarily show up in the Fourier, in the harmonic domain. So there's no dispersion relation. that for some reason these booster columns do not produce in the numerical simulations. So the question is, are they weak? Are they absent? And what does this mean for the convection zone? Right. So finally, I think I've detected them, and I'll show you the results. So this paper's been accepted, so it's in print. I haven't put it up in archive. I actually lost my archive privileges. I have to go and ask someone to approve my, um, the ability to upload an archive. But okay, so basically both HMI and GONG show these prograde dispersion relations. These dispersion relations were predicted again a very long time ago by all of these stalwarts, Busse, Gilman, Glatzmeyer. All of these scientists have shown or predicted different types of prograde ridges. Oh, sorry, jumped a couple ahead. And they so I see them as well. They're very weak, but you'll see them. I hope you'll see them. And yeah, so I see them in these S minus T, 1 S minus T. So S is harmonic degree of the perturbation. The reason why I use ST is that LM is primarily used to describe the modes, oscillation modes, the P modes, and S and T are the wave numbers of the perturbation. So S minus T 1 is antisymmetric across the equator. S minus T is 3 is antisymmetric across the equator, but with nodes, right? There's 2 nodes, and 5 has 3 nodes, or whatever. So these are the, or 5 is 5 nodes, sorry. And so these are different vorticity channels, which spatially they whatever in the harmonic domain. Okay, so here's the result. I want to take you through it slowly. So there are these are two different plots. They look identical, but they're different. And there's HMI, there's GONG plus plus. On the horizontal axes, let's focus on this one here. If you can't see my mouse cursor, please tell me. The horizontal axis is T, which is harmonic degree, and T goes up to 75. So first of all, I want to say in helioseismology, there's no one's really ever gone up this high using spherical harmonics all the way up to 75. So that's one of the incredible benefits of using normal mode coupling, is that you can very cleanly go up to high wave number. So these are all, each column corresponds to different S minus T. So here T is varying, so obviously S is varying, but S minus T equal to 1 has to be obeyed. And S minus T is 3, 5, and 7. So these are all antisymmetric Busse-like columns ostensibly. I do not have access to this. I don't know how this looks like in the spatial domain, because one of the problems, as I said, with normal mode coupling, with same L mode coupling, is that I can only measure odd S. So I've kind of removed the odd S channels here, compressed the this x-axis. There's no odd S. Sorry, I can only measure it at odd S, so there's no even S here in this. So that limits my ability to take these measurements and transform them into the spatial domain. So I can't really tell you if it's localized in this around the equator. I can't really tell you very much about how it looks like in space, but I can tell you that there's a nice dispersion relation which you hopefully have seen by now. So you can see it in GONG, beautiful. It goes all the way seemingly up here. You can see the same thing in HMI, a little fainter some places. You can see it here. You can see it here going up. So you can see it virtually in all channels, maybe not S minus T of 7. So it's more localized to the equator. That's what this means, if S minus T equal to 5. If you were to believe me, or if you were to naively consider this, that's what it would say. Then the other interesting thing is that there is this feature here, which is this high frequency Rossby mode that was detected by Hansen et al. In 2022. That seems to be moving into the prograde domain, very weak. So I haven't identified it. I'm just telling you, by voice. But it seems to be, moving into the prograde. Now, the reason why this is really important is Yuto Becky wrote a paper 2 years ago or a year ago, and he said that if this were to become prograde, then that would imply that the bulk of the convection zone is actually subadiabatic, faintly subadiabatic. So so that would ostensibly have important implications that this thing is traversing the zero frequency line and crossing into the prograde. Then the other strange feature is this thing here, which is looks like an Alfvén wave actually to me. I don't know what it is. I don't know what this is actually, but I just assumed it's U is an alphane wave. Uh, then the last thing I want to say is that there seems to be one thing here. There seems to be another. I have not described, I mean, I've speculated that it could be something else, but again, it's not a conclusive detection. Is that there's a second feature here parallel to this, which almost looks like like how P modes go in radial order. So these are convective cavities at different radial orders, basically. Again, predicted by theory. So it seems like there is another one that's sitting here. Okay, so this is one mode combination. So I use modes from 70 to 200, the harmonic degree 70 to 200, and this frequency range. Well, all the modes have to lie within this frequency range. And a tracking rate of 456 nanohertz for this. But when I change this mode sum, I use the same harmonic degree range, but I reduce the upper frequency to 2500 microhertz. So these are even lower frequency modes. So you see that this one seemed to go from 0 to 400, but this one now seems to saturate at 200 nanohertz. So I think it's most clearly seen perhaps in this one, in S-T of 3. And you can see this thing sort of flattening out here. Again, a beautiful prediction by Gilman and others. Sorry, is there a question? What are the vertical streaks? This is So this is part of the problem with I've taken the. I imagine you mean these weird splotches here. It's honestly got to do with the fact that I only see odd S. So I've sort of cut some parts of the spectrum and pasted it here. So I've cut out all the even S, and so it doesn't look very smooth. But it's nothing to worry about because this has been independently verified. Like the HFR has been independently verified. There's a Rossby mode that you're not seeing here, but the Rossby mode has also been independently verified. So the splotches occur in all of this. It's a weird mode coupling thing, and that's the reason for the streaks. Yeah, so this one seems to saturate at 200. Now, there's a very beautiful, I think the first measure or the theoretical prediction was by Gilman and Glatzmeyer, 1981. They wrote a sequence of 3 papers, which I've read like so many times and looked at those again and again. But a lot of those actually looked at, and in fact, even Becky, sorry. Yeah, even Becky and others, maybe Hyman and Jane, they've gone to much higher wave number, but most other studies, and Bloom, I think, has also gone to much higher T. But most other studies have focused on this low T thing. So in fact, a lot of the previous work has the modes seem to go up to 456 nanohertz within the first 10 in harmonic degree, or in azimuthal order. But this one seems to be much more steady, much more in terms of low frequency actually than the other things. And so there are implications for this in terms of how deep they are and so on. So I don't know how much time do I have. Okay, I have 30 minutes. Okay, good. I'll be done in another 10, 15 minutes. Um, so where are these modes, right? That's another question that you'll probably ask me. So one of the things is that I've kind of mixed all the modes together to image this. So it's very hard for me to really say exactly where they are. What I did though, to sort of constrain this a little bit, is I looked at only F modes, so L of 200 to 300, and I look at F modes only. And this is the power spectrum associated with these F modes, S1, ST of 1, 3, 5, and 7. And there's no indication at all, maybe a little bit here, of these thermal Rossby modes. They're basically gone when you use only F modes. And if you look at the sensitivity of the F mode, that's this dot dash blue curve. They're primarily located in the upper 2%, and the sensitivity dies very quickly deeper than that. But the other two mode combinations that I've used, they penetrate much deeper. So my speculation is that all of this signal that we're seeing here, all of this really weak, faint signal, is coming from layers below 98%. And they're all sitting here, and they're probably decaying very rapidly in the near surface, highly turbulent region. And what's very interesting as well is that they inhabit the same wave number region. So supergranulation goes down to 30. Okay, 30 may be a bit of a stretch, but at least till 50, and goes up to 150. But we're seeing some of these features go up to 75. So it's very interesting that they occupy the same region. They're not seemingly uncoupled, right, from supergranulation. So I'm not quite sure what's happening there. So that's one interesting feature. And if these are, I mean, Heinemann and Jen suggest that any prograde feature like this basically is a thermal mode. So now, if you were to believe that these are thermal modes, and you use their mode amplitudes can be used to estimate the Rossby number, then we're at this rotationally constrained convection zone, which is 10 to the minus 4 to 10 to the minus 3. That's the number that I arrive at if you would, if you were to believe that these are thermal Rossby modes. And each of these, as I said, represent different cavities ostensibly. This is 200, this is 400 nanohertz. And this is an estimate that Heinemann and Jin provide for different, for the upper and lower turning points. And so this is sort of where they're sitting. This is the lower turning point, this is the upper turning point. And you could read the paper for more details, but this is the region for all these different S. This is the region that they're sitting. Both the modes, actually, interestingly, both the modes are roughly sitting in this region. So the high L stuff is sitting close to the surface. The high S stuff, sorry, it should be T actually. High T stuff is sitting close to the surface, and the low T stuff is penetrating much deeper and penetrating all the way down to the base of the convection zone. So with that, that's the first topic. Now I have give me 8 to 9 minutes and I finish the second topic. Again, a very important topic. But I'm not that excited by this. But it's a nice result though. But I just wasn't so happy with this result. The first one really lovely. Anyway, so okay, I've already said what these are, and this Rieger periodicity is something that's been measured quite recently. So okay, so the primary the smoking gun, so to speak, of these magneto-Rossby modes is that they induce mode splitting. So this black, this is temporal frequency, this is azimuthal order as before. So the black curve and the black asterisks indicate a hydrodynamic Rossby mode, the Rossby orbits. And if you take this 2D shallow water model that Zakarishvili and a variety of others, Gilman, Dikpati. Again, I have not cited people, but there's a lot of people who worked on this, and they've really studied this model very carefully and done many more complicated models, not just 2D, but studied 3D, for instance, Dikpati and so on. And so if you induce a weak magnetic field, so this is a 2D model, so I call it surface field, but it's a strange configuration. So it'll become clear why I've chosen the strange configuration, but it's basically something like a field that is centered around 30 degrees in both hemispheres, but flips. It's antisymmetric, so it's negative in the southern hemisphere and positive here. But because the dispersion relation only depends on b squared, so it only depends on the unsigned field. That's the quantity that matters. Then that introduces the splitting. And you see that these are slow modes, the canonical slow Rossby modes, slow MHD inertial modes, and these are fast MHD inertial modes. And so this is what I consider to be a smoking gun. And I was not looking for it, but I found it actually, seemingly. Very blurry, I apologize. There's some smoothing that's gone into this power spectrum. So this is S equal to T. So this is symmetric. The vorticity again, solely vorticity. And it's from 15 years of HMI. And yeah, so this is just an S equal to T. You see this thing where the mode seems to come up here and then seems to split. Now, first of all, I want to say that the splitting here is different from the split. Sorry about that. Sorry. This splitting goes at 0 frequency and climbs, and this splitting goes like this. So this splits differently, huh? So that's the first thing. So I'm not 100% sure that these are magnetic, but I feel like that's the best case explanation for what's going on here. So most prior seismic studies why has no one else detected this? So 20 is where they've typically stopped. Okay, you can go a little bit higher, but a lot of the ring diagram stuff that people have done before have primarily have modes that are focused near the surface, or at least the first several megameters, 10, 15 megameters. Again, the reason why I'm able to see it is that I'm using the same mode combinations that I described earlier, and these have tails that go much deeper. And so this my theory is that these modes be sitting there. There's like a ton of modes sitting below in the deeper interior. And we're not seeing any of these because this connections, the outer 2% of connection is destroying these mode coherence or reducing their amplitudes enough that you wouldn't see it. Sorry. And so now if you fit this and this, and that's this cyan line and the red line. And that's why I have this funny field configuration, because that's a fit to the observations. And you would see a surface field of 5 Gauss that would induce, if it were at the surface. Now it could be deeper down, it could be at the base of the convection zone. I believe that would be 5,000 Gauss roughly, because it goes as square root of density. So at 5 Gauss at the surface could induce a splitting whose asymptotic slopes here, this is the asymptotic slopes of the slow and the fast Rossby modes, are comparable to the cyan and the red lines here. Now, one of the questions you ask is how trustworthy is this? I mean, this one at least it's strong, but this one's kind of weak. So I did a comparison with Gong++. And also to detect time variability, right? You would expect that if it were magnetic, you'd see time variability. So there is time variability, but it's not obviously correlated with the cycle in any way. I don't know that I could say that. But all of these seem to show, the gong seems to show this splitting. You could see it sort of coming down here and maybe stuff here. But this is really becomes quite grainy at this point. This is a weak signal. This is not a strong, sharp signal. So HMI is the clearest. Gong isn't bad either. You could sort of vaguely make some stuff out here. Certainly the prograde ridge is visible in almost all of these. Maybe not so much this. Yeah, this is what I was saying. So if you use only modes within 100 to 200 and you use all modes, then you see this very nice splitting. But if you use F modes, it goes away. This is 190 to 300. And so this is all the modes. It's this blue line. It's penetrating quite deep. And this is just the F mode. So the top 2% do not contain this, which may explain why no one's seen some of this stuff before. And so that's it. That's the end of my talk. There's actually, I haven't shown all the things I've seen, but there's many other really remarkable, very complex oscillation spectra that I saw in this. And I just want to say one thing. I'm going to revive. I mean, maybe it's, I'm being overly confident, but I think there is the possibility that I might be able to. I don't know that I will. I mean, in all likelihood, I will not be able to do it. But G modes, for instance, if it were subadiabatic, I've been speculating that then the G modes will penetrate much higher. And there's a way to that you can use mode coupling to go up to 200 and 300 microhertz, actually. So this is all half a microhertz. It's 456 nanohertz. But you can use G mode, the mode coupling to measure things that are operating at 200 and 300 microhertz, all the way up to 500 microhertz. That's my limit. So I'll let you know how that goes. I'm trying to do this high frequency imaging now. So with that, thank you very much.
Thank you, Shravan. Very exciting results. Questions? Gilbert?
Yeah. Could you go back to the early formulation? One of the early slides.
Yes.
I'll recognize
Which
it when I see it. All the way
Which
back
ones? Yeah, sorry.
to the original formulation.
Which formulation of what? Sorry, the thermal Rossby mode or the mode coupling or what?
Mode coupling.
Oh, right. This thing?
Yes. Okay. So I was puzzled when I looked at it because you're also coupling M prime with M. Now,
Yeah.
Even in the rotating case, it separates by M. So you have modes that aren't coupled in longitude in that way. But in what you did after that, you didn't show anything about M coupling. It was all L and T and so on. So I'm thinking that, in fact, I mean, if M's are going to be coupled, that's a truly nonlinear system. But you're looking at
No, no,
linear
it's
measurement.
sorry. It's I'm sorry. There's some misunderstanding. The T is the difference between M prime and M. Yeah, so this is basically when you write this out in spherical harmonics and
Yeah.
then into generalized spherical harmonics, you get a difference M prime minus M because it's e to the I M prime T minus e to the I M. It's e to the I M prime phi minus e to the I M phi. So that correlation gives you this. And so that M prime minus M appears as a T here. So the
Mhm.
reason why M and M prime couple is that you have a non-axisymmetric spatial scale or inverse spatial scale T. That's the reason M prime and M couple.
Okay, so you're saying it's different from the point about these all being linear modes. See, when
It
I
is,
think of
it's all linear. It's all linear.
right, but see, when I think of M prime coupling to M as a fluid dynamics problem, that's nonlinear for me in terms of angular momentum transport and all those kind,
Ah,
producing
right.
different modes. You follow? Yeah.
Yes,
So
I
it's a
understand.
fundamentally different point.
Yes, that's right. So if you consider this linear system and you express this in terms of its eigenfunctions and you follow through with the mathematics, it all comes out very cleanly. There's no complication. But
Yeah.
I understand your point that in angular momentum transport, M prime M is a nonlinear coupling.
I
Yes.
mean, different modes of different L do couple uh,
Yes.
as soon as you have rotation. No question about that.
Right. Right. That's right.
Okay. There's another question from the Q&A from the attendee. Uh, so, Saprabha asked about the difference between the two plots for the thermal Rossby spectrum.
One second.
Can
It's a bit grainy. I understand why there's a confusion. So the referee was also quite confused. They thought it was identical. No, these four panels, 4 by 3, or 3 by 4, is one cavity, and in my sort of view of this represents one cavity, and this represents a second cavity. And so in this, for instance, you see this thing saturating at 200 nanohertz. All of these modes basically saturate at 200. You don't necessarily see it all the way through in every single panel. For instance, in this case, the S minus T equal to 3, you see it, sort of going out far. But in this case, it keeps going up. So it goes up almost up to the window. So 400 and something nanohertz. So this one's going across from bottom to top, or from the middle to the top. So that's the difference between the two.
So Prabhat, has that answered your question? If you want, you should be able to talk.
Yes. And I just wanted to ask a question in relation to Peter Gilman's question. So is the thermal Rossby mode is
Mm.
a nonlinear perturbation to the acoustic modes? Yep. That's essentially what you're measuring.
No, not at all. No. It's all linear. It's completely linear.
You measure the amplitude of the mode. Yeah, and you do this because the mode has a finite amplitude. It's a nonlinear perturbation, which the acoustic modes are sampling.
No, not at all. Not at all. It's like how you can use seismometry to measure the amplitude of a flow, like rotation.
Yeah, and that's because the flow has a finite amplitude. The
Yeah,
flow is a
yeah.
nonlinear background perturbation, and the two waves are coupled by that background interaction. In that sense, it's a nonlinear. It's not important.
Yeah, okay. Oh, yeah. It's a triple integral of three generalized spherical harmonics, if that's what you're saying. And so that's how the three talk to each other, two waves and the perturbation.
Yeah,
And
and then,
I don't know
yeah.
what you mean by nonlinear, but yeah, okay.
Another hand raised. Krish Mandu.
Hi,
Hi, Krishna.
nice to see you. So,
Likewise.
why do you start your analysis from harmonic degree 100, not all the way to zero?
I know, honestly, it's a trial and error, right? So I did a 15-year analysis all the way from 30 to 300. So that
Mm-hmm.
was my sample. Sorry, I don't know
Mm-hmm.
why I'm flipping. But I did it from the entire thing from 30 to 300. And then
Mm-hmm.
I just spent a few days looking at different mode sums. I said, what happens if I do 7? So this particular mode combination, 70 to 200 gave it to me. And the other
Mm-hmm.
ones, it didn't appear so strongly and stuff. So as I said, like if you look at just F modes, you don't see this at all, for instance.
Mm-hmm.
So I
Yeah.
mean, there's some way to do this much more systematically. I have not done it systematically. I thought I was going to exit the field, but then I discovered this, so now I've returned to the field.
Okay, nice result.
Thank you very much.
You too, Becky, you have a question?
Yes. Hi, thank you for the talk. So in the slide you show many power spectra for thermal Rossby modes.
Mm-hmm.
So what are so they are very faint green dotted curves.
Yeah,
So
that's the dispersion relation fit to it.
so it's a fit to the observation. It's
Yeah,
not
yeah. So this is
observed.
HMI. This is just HMI, and I've just done the fit with the green just to draw the eye to this thing. And then I've shown the same plot without the green thing so that you can, so I've biased you, right? So now you're expecting to see something there, and so you see something there.
Mhm. And on the right, it seems to so it seems different, right?
Yeah, it's a different ridge. It's a different
uh,
ridge. You expect a family of ridges. If you go back to Gilman and Glatzmeyer 81, you'll see that he shows these different ridges.
yeah,
It's
yeah,
like,
yeah.
yeah, it's a P mode comb, frequency comb. So you expect to see different ridges like this.
Okay. Okay.
You expect, honestly, it has to be much richer than this. There's probably a lot more modes. As I said, I've seen a lot of stuff in my analysis. I don't have time to write these papers, but I see so many interesting things. Like you see this thing, right? This thing cutting across, and then there's one in which this thing comes down, and there's some really complicated stuff going on here. Actually, there's a lot of really complex dispersion relations sitting here, but we're not seeing it because they're not at the surface. They're deeper down.
Okay. Thank you.
So I just want to say one thing that I forgot to say, that I wonder if this implies that the solar convection zone is actually subadiabatic most of the way, or poised at criticality. It's not strongly superadiabatic. Well, some people have thought that for a while, but it may be even more subadiabatic than we thought, which might be a good case for G modes extending higher up into and other interesting physics. That's the one note that I forgot to mention.
Krishnendu, have another question?
I have one more question. So why do you say Gong is performing better than HMI, or are they comparable? Like,
Yeah, they're comparable. I mean, I don't see any difference. I mean, it's recovering all the same ridges.
mm-hmm.
Uh, in some cases, it seems to do a little better than this. Like this one, it seems to. I don't know. It's comparable. I just
Maybe Gong has like more time series. Like you can start
no,
from.
this is the exact same time window, 15 years.
Okay.
I did average more, and
Mm-hmm.
no, it's in. But then when I told my Laurent and I told Aaron and others, they laughed at me because they said, "Of course, Gong is as good as HMI." So it's very
Mm-hmm.
very good. It's very
Mm-hmm.
very good. I just assumed that it wouldn't be as good, but that's a
Mm-hmm.
false assumption.
Okay, any other? Oh, Roba?
I have one more question. So here you mentioned one of the ridges crossing zero, but you can move the ridge by just changing your frequency, no? Your
The
reference.
track You mean?
Yeah. Yeah.
Yeah, you can change the slope if you change the tracking frequency.
Yeah.
Yeah.
Yeah. So when you talk about this ridge crossing zero, what does that mean?
Yeah, I mean, there's definitely some, I mean, there's some range of possibilities. I mean, you could go from I suppose you could go from 430 to 440 to 450. I mean, you don't have too many choices for rotation rates. It's not like it's wildly unconstrained or something. There's a small range. Within that range, these things are firmly prograde. So they're not going to suddenly become retrograde.
No, I mean the ones underneath, the second ridge you were talking about.
You mean
Yeah,
this thing?
the HFR ridge.
Oh, this one. Yeah, what about it? Oh,
Yeah,
you mean this thing crossing over?
yeah, I thought you were saying that was important.
Yeah, I think it is important. I mean, but it's faint. I need to detect it more. I mean, if you change the tracking rate, it's just that the slope will become shallower or sharper. But
Yeah, but
this crossing will not. I mean, it'll still keep going.
yeah, okay. I mean, if you change the slope, you don't have to change it much for that one to not cross. No?
I think, yeah, I mean, it's a good question. It's not observed very cleanly, but I think it goes to substantially far out. So changing the slope by a little bit will bring it down here, but okay, anyway, this is to be discussed.
Okay.
Yes. Yeah, it's okay. Maybe you're right. I mean, I don't want to argue this point because I'm not seeing it that clearly.
Okay, there's now another question in the Q&A chat by Suprabha. The question is, could the Rossby mode reach for m larger than 20 be n equals 1 Rossby modes as compared in Hansen and Hanasoge 2024?
Could be. Sorry, I don't know about the radial order mode identification stuff. It could be. And we had a talk about this in Berlin. Sorry, I don't know the answer to that question.
Okay, any other question? We have like a 5 minutes left. If no other question, let's thank the speaker, Shravan again. Wonderful results and very exciting new findings. And thank you for all the discussion, and for all people who attend the seminar at this irregular time. And thank you, Shravan, for staying very late to give us this seminar.
Right.
So this talk has been recorded, and as usual, it will be put up on our COFFIES website afterwards soon. If anyone want to watch the recording again, or any of your colleague missed the seminar and want to see a recording, please reach out to me or go to our website after this seminar. Okay, so hope to see everyone again next month in our next seminar. Thank you, Shravan, and bye.
Bye. Thank you.